So many major breakthroughs in biomedical research, from understanding how cancer spreads to gene editing with CRISPR, depend on something that most people have never heard of: a glass microneedle. Microneedles, as the name suggests, are incredibly small needles with diameters as low as 15 microns. That's almost 10 times smaller than the average human hair. Whenever a researcher needs to inject a tiny amount of liquid into a small biological target, they make these needles by hand in their lab, leading to inconsistency from human errors. And this is not the only problem. These needles clog easily, either from debris in the delivery liquid or from biological material that gets stuck in the tip during insertion. Either way, to unclog these needles, if it's even possible, wastes both time and expensive material. In order to solve this clogging issue, my lab redesigned the needle to have a solid point and holes on the side, which is both sharper and prevents clogging phenomena. However, this new complex shape is incredibly challenging to manufacture using normal methods. And so we turned to 3D printing, specifically a type of microprinting called direct laser writing, which uses a high-powered laser to solidify material point by point, allowing us to make structures as small as a grain of sand. The materials that are normally used for direct laser writing are called polymers, and they're somewhat flexible, and this includes plastics and rubbers. But normal microneedles are made of glass, which is much stiffer. My research asks a simple question: can I 3D print this anti-clogging microneedle out of glass? The answer was no until 2023, when researchers developed a new material for glass 3D microprinting, primarily made of polyhedral oligomeric silsesquioxane. That's up to 600 points in Scrabble, or POS for short. This unique molecule can be combined with the components of a normal photoresin and printed in the exact same way. But after printing, I place it in the oven and I bake it at 650 Celsius. That's 1200 degrees Fahrenheit. The organic components burn away and leaves behind a pure fused silica glass microneedle. To test these needles, I chose to do it in zebrafish embryo because of their common use in biological research. My needles were able to successfully puncture the stiff outer membrane of the embryo, called the chorion membrane, and deliver gene editing CRISPR to over 200 embryos with the same needle, which is how it's done in labs today. Even more interestingly, we noticed that the membrane of the embryo moved less during puncture with my needle compared to the standard laboratory needle, which could theoretically improve survival rates, a hypothesis that we are currently investigating. With the recent developments of 3D printed glass, not only can we reinvent the microneedle, but any glass microtool can be redesigned into shapes that were previously thought impossible, enabling better and faster research through adaptable biomedical tools.